Great. So just a quick couple slides. First, how to get the most out of the event. So of course, we're running this as through Zoom, but also through this Whova platform. And I encourage everyone to make use of this as much as they like. You can do things like upload a profile so other attendees can find you and send you messages and network. There's virtual coffee breaks that we'll have in a little bit. There's also a community board where you can join some discussion topics or start your own topic or even social groups. And just one other point is if you do require a certificate of attendance, please just email me after the event or feel free to just send a message through Whova. So during the presentations, we are running this as a Zoom meeting instead of a webinar. Because during the breakout sessions, we would like to give everybody the opportunity to discuss and unmute their mics and have good discussions with the presenters. However, during the presentations, please do leave your mics on mute and your videos off. For any questions, feel free to submit them through the Whova app. There's a Q&A section for each session, but feel free to also use the Zoom chat if you have the Zoom meeting open separately. We will moderate both, so that will go fine. If you find that your question does not get answered, then I encourage you to join one of the virtual coffee breaks or the networking after the meeting. Or please find the speakers directly within the Whova app and you can send them a message that way and they will hopefully get back to you. And then one other point of encouragement is to definitely use the chat functions within Whova or Zoom. Introduce yourself, feel free to post your email, tell what you do, just so we get to know a little bit about who is on the call today. And one other point, so for these virtual coffee breaks, we have one coffee break and then networking after the meeting. If you go within Whova, you can, to get to these coffee breaks, I should say, you can go to the community tab and then you will see that is here and you'll see a place to click for meetups and virtual meets. If you click there, then you will see the various coffee breaks that we have set up. So I encourage you to join and discuss with other attendees. And with that, I would like to hand it over to Anka. So Anka Anastopol is a research scientist at TNO in Delft. She has a background with material science and energy storage research. And she is currently the overall coordinator of the E2C project. And she will give a brief introduction to the project. So Anka, I will hand it over to you.
Thank you very much, Erin. And thank you for organizing the event. Yes. So first of all, I'd like to welcome you to the event that we have today. Some of you have attended the previous events that we have organized. The event today is part of 3 events that we have organized to present the results that were generated in the project Electrons to Chemicals, which was funded by Interreg E2C, but also by Sparkport, by the province of South Holland, the province of North Holland, and the Ministry of Economic Affairs in the Netherlands. A few things about the project. A few years back, partners from the region, which we call E2C, have come together and they have formulated a project proposal which has as the main objective to stimulate and to support companies to further invest in the development and implementation of Power-to-X technologies, but also to accelerate the transfer of this innovation to the market. And this is an important thing to notice, that the project does not only advance technology, but it's also, it looks at the market dynamics and how these new technologies can be implemented. The consortium which was formed was was combining the chemical industry and the large wind parks, was looking at the combination of the chemical industry and the large wind parks in this region of Northern Europe around the 2Cs. And they have identified that there is an opportunity to bring these Power-to-X technologies closer to this to market readiness, and to contribute at the same time to the sustainability goals and to increase competitiveness in this area. Therefore, we have been working in the past few years on developing a lifetime testing station for novel electrolyzer concepts, highly flexible pilot installations for the direct conversion and utilization of carbon dioxide. Also developed flexible pilot installations which will be available also after the project for cross-border testing and innovation for the synthesis of dimethyl ether for electrolysis and for carbon dioxide electrolysis to formic acid. Moreover, this link to the market is done by in the project by looking at the feasibility studies for the implementation of the technologies in the 2Cs region. And this will be also the focus of the event of today. What are the results and how what are the findings of the from the project on the one hand, and on the other hand, how our guests and key speakers are also looking at these issues from outside of the project. The problem that we are looking at now, and we are trying to solve on a greater scale, looks at not only technology development, but also challenges the origin of the energy resources and the carbon resources that are going to be used. And in order to develop and to implement these technologies, we have to be aware that it is necessary to couple different sectors. So the energy sector will be very important to be coupled to the chemical sector. In this world of carbon dioxide reutilization, it's also important to look of where the electricity is coming from the renewable sources, and then again to create these valuable chemical products which can be further used in the chemical sector. Therefore, we are trying to link these different sectors at the level of technology development, so at the very basic level, but also to think of how to bring them further, and how to connect them also in a terms of life cycle analysis, in the terms of economic evaluation and business cases. Coming closer to the event of today, we have three keynote speakers who come from outside of the project, and each of them are going to give us their perspective on the different on these different aspects. We have Arne Kettelhon, which is a co-founder and managing director of Carbon Minds. We have Carl van der Grift, managing director for Galore, and Jeroen van Woerden, strategic advisor of Field Lab Industrial Electrification. After hearing our keynote speakers today, our partners from the project will try to engage them and engage us into discussions around the key topics that the project addresses, and which are very relevant in the development of these new technologies in the 2Cs area. We are also going to present what the developments in the project are, and how and what our key findings are. And I also very much hope to meet you all at the virtual coffee break for even more interaction and to exchange ideas further on these topics. This being said, I wish you a very pleasant afternoon at the event, and I give the floor back to you, Erin.
Great. Thank you very much, Anke. Good. So I will just introduce our first keynote speaker. And Carl, go ahead and share your presentation. So Carl van der Gift obtained his PhD in chemistry from the University of Utrecht. He then started a career in catalyst R&D, catalyst manufacturing, and catalyst business management that took him to Shell, CRI, and Porocel. He then joined Albemarle in 2010, where he became the division vice president of hydroprocessing catalysts and served on the boards of Eurocat and Nippon Ketchen. Since 2016, he is the director of Catalyst Intelligence, which is a consulting company that provides independent advice to refineries, petrochemical plants, and catalyst manufacturers. Since 2020, he is also co-founder of Galorus BV, a Dutch startup company focused on the reduction of gas flaring. So Carl, the floor is yours.
Well, thank you very much, Erin, for this kind introduction, and good afternoon. Galorus stands for gas to liquids on-site, onshore, I should say, redeployable kits.
Carl, I'm sorry for interrupting you, but we don't see your presentation.
Oh, let's
or
see.
You actually.
Or me.
Now we
what
see you.
Here? Now you see me, but
yeah.
I had actually, I thought I had uploaded it. Let me try that again. I should probably say here. Oh, wait, I'll cancel. I go back here, sorry about that.
No problem.
Share screen. Decide what you want to share. This one, share. How's this?
It's just loading. It's perfect. We see now in the PowerPoint, we don't see the presentation view.
Yes, I go to presentation view. Is it okay?
It's still showing the PowerPoint. You might have to share the actual presentation view usually.
I can only say I can stop the sharing, which I don't think we want to do, or I can hide it.
I think you can stop the share, and then you probably need to select the actual presentation.
Presentation form here. Yeah. And now I go back to the Wova. I go share screen again. Let's see what no, it doesn't take it.
Okay. Would you prefer?
I can make this a bit smaller here on the side.
Yeah, if you want to do that way. Otherwise, I can share it from my computer as well.
I made some last-minute changes, so let's do it like this.
This looks fine. Yeah, we see it just
All
fine.
right.
Thank you.
Well, thanks for that. So Galorus stands for gas to liquids onshore redeployable skids, and that's what we want to develop. And the Galorus company, startup company in the Netherlands, is developing a mini GTL solution to take the associated petroleum gas and stop flaring by producing synthetic crude. And I founded this company together with Ki Chen, and I will introduce him later. So the presentation is divided into 3 parts. First, I will talk about the problem of flaring and why it should be stopped. Secondly, I will talk about the Galorus solution of gas to liquids. And finally, I will talk about challenges that we face and adjacent opportunities that we see to deploy this gas to liquids technology in Power-to-X, which I think is interesting for this seminar. So if you look at the world map, here a satellite picture, you see the flaring as bright spots. This is going on 24/7. The associated petroleum gas is coming out of the ground together with the oil. The oil producer does not always have a solution for the gas, because there is not always a gas takeaway, as it is called in the industry. And where there is no takeaway, the producer decides to flare. And this is really has been going on for many, many years. And of course, with the increased production of oil, also you see flaring increase. Major countries where flaring is occurring are Russia. In the Middle East, it's mainly Iran, Iraq, North Africa, Algeria. Then you have Venezuela and South America, and then Mexico, United States, and Canada. So it's a global problem, major CO2 emissions, and even to make things worse, there is some uncombusted methane leaking as well. Estimates range from 2 to 10%, because these flares are certainly not providing full combustion. So major problem. If we try to quantify it, here are some numbers from the World Bank, 2019. We see that about 150 billion cubic meter of natural gas is flared annually. And these numbers have been fairly constant over the last couple of years. Only a small dip in 2020 due to COVID, but everybody is afraid that the number for 2021 might be back at the historical level or even slightly over. If you convert that into heat content, that is 5.3 billion MMBTU. And if you look then at the economic value of that gas, that will be $13.2 billion that is being combusted annually without any economic benefit whatsoever. So it's a huge economic waste. But apart from that, there's also significant CO2 emission, as you see here, more than 400 million ton CO2 annually being emitted from these flares. And then you wonder, well, why is nothing being done about that? There are, of course, solutions, sort of. And you could capture that carbon at the wellhead, because it is coming available rather concentrated form. If you would capture it and convert it into other products which you could bring to market, you could generate additional revenues. Nevertheless, these solutions are not implemented to any significant extent so far. And we see that the barriers for implementation are that flaring, of course, is a known technology. It's well established, it's simple. The operators, they like it, it's cheap. Operators also consider that any small-scale carbon capture is complex, and they don't see the benefit of that. And furthermore, in some of these countries that I mentioned, they have rather weak environmental regulations and poor enforcement. So these things are all contributing to a lack of implementation of any abatement technologies. However, the times are changing. I think the world is certainly aware that we need to do something about CO2 emissions, and this is seen as a major source. And the World Bank has started this global gas flare reduction partnership, where governments, national governments, sign up and commit themselves to implement stricter legislation and to monitor compliance. And oil and gas companies also commit themselves to stop routine flaring by 2030. So the industry is moving away from the flaring, but there's a little implementation so far. Another tool which I would like to mention here is called Flare Intel. It's a monitoring tool developed by Capterio, a UK-based company. And they make available all the locations of the flares, including the total amount of flare gas that they have been emitting, not only of this year, but also of prior years. And they also name the operator for each flare. So that gives good visibility on who is flaring and how much they are flaring, so that governments and other institutions can look into what's happening and where they should focus their attention. Now, Galore is certainly not the first company to look into solutions. Many other startup companies have looked into this problem before. Some have been successful, and we see some deployment of small-scale flare abatement, but many others have failed, run out of money, or run into technological problems and never made it to commercial deployment. So when Chi and I were looking for a challenge a couple of years ago, we decided that this was a nice topic for us to look into. And then we started Galores. So Chi has a background as a chemical engineer from the University of Ghent in Belgium. And myself, I'm a chemist from the University of Utrecht, and I've always worked in the catalyst business. And so far we are just 2 people, but when we have a need for additional work to be done, we will certainly hire additional engineers. So Galores, the original idea was to go gas to liquids. And in the meantime, in this 2 years that we now exist, we have actually already thought of 3 solutions that we would like to provide. But today I will mainly talk about gas to liquid. So here you take the flare gas, mainly you are interested in the methane, and you convert the methane into synthetic crude, which can be transported to a refinery via existing oil infrastructure. So realizing here that the operator of the well is interested in oil production, we thought we will make a product which he's interested in, and we will stop the flare by doing gas to liquids. Other solutions that we look into are blue hydrogen production. So here you would take the flare gas, produce hydrogen via methane reforming and water gas shift, and then separate the hydrogen for use as an energy carrier, and the CO2 you would re-inject into the well for enhanced oil recovery. So that is something we're working on. And finally, we're working on mini LNG plants where you would take the methane, liquefy it, and bring it to market by truck or barge and sell it to LNG consumers. But today's presentation, we focus on the GTL. Now, very simple flow scheme. As I mentioned, we start with the flare gas. It may need to be treated like removal of sulfur. There may be mercury, there may be natural gas liquids. So there is some pre-treatment. Then the gas goes into the methane reforming, where we will produce CO and hydrogen, so-called syngas. The syngas is sent to the Fischer-Tropsch reactor, where we produce liquid hydrocarbons. And then the products are separated. The desired product of the hydrocarbons are sent to the crude pipeline, and the other components like water and Fischer-Tropsch gas are recycled into the system. So the methane reforming, of course, is a well-known technology. It has been around for many years, and several suppliers offer those processes, including catalysts. Fischer-Tropsch has also been around for many years, so these are all known technologies. And what we bring is that we integrate them in a certain way whereby we achieve very high carbon efficiency. Before we look into that, let's look into the chemistry. So here we have the methane reforming. Steam methane reforming is the conventional reforming, let's say. You produce CO plus 3 hydrogen. But recently has been in development the dry methane reforming, where you use CO2 as the oxidant, and you produce CO plus 2 hydrogen molecules. Now you need to be careful because the catalyst needs some water to avoid coking. And therefore these processes are usually combined as a steam carbon dioxide reforming. More easily we talk about mixed reforming of methane. The objective of this step is clearly to produce the syngas. Now side reactions are the water gas shift and the reverse water gas shift, as well as carbon deposition by either methane decomposition or the boudoir reaction. Of course, these last 2 reactions are certainly something that you want to avoid because it will coke your catalyst and stop your process. So you need to be careful with temperature, pressure, and catalyst selection, and make sure that there is enough steam to keep the process progressing. Now, once you've got the syngas, you go to the Fischer-Tropsch, and there the CO and the hydrogen react to usually long-chain hydrocarbons, saturated and unsaturated, plus some water. As you see, for every molecule of CO that you convert, you form some molecule of water. And there can also be some oxygenates being formed. In addition to these desired reactions, there is also the water-gas shift, and that would take CO plus water going to CO2 and hydrogen. So in the Fischer-Tropsch off gas, you also see CO2 and hydrogen. So in combination of all these reactions, we see then the Fischer-Tropsch products that are the desired hydrocarbons, liquid hydrocarbons, as well as some light hydrocarbon gases. There is Fischer-Tropsch water, and there is CO2 and hydrogen. These processes have been used on a commercial scale by Sasol and Shell for a long time. They start from either coal or from natural gas. They produce syngas, and then they go to liquid products, and they have installations with 14,000 to 160,000 barrels a day, so really large-scale industrial plants. Much larger than what we are looking for to stop a flare. So our objective here is to make this whole GTL much smaller than the existing commercial units. The catalysts for Fischer-Tropsch are well known. It's either iron-based or cobalt-based, and different reactors are being used. Can be a fixed bed tubular reactor, can be slurry, can be fluidized bed. Gas Galores has chosen the fixed bed tubular reactor because it's relatively simple and easy to put into a module, which we can then bring on site at the flare. Then, of course, we did some flow sheeting together with the University of Ghent, a group of Professor Mark Sijs and Marianne Flores-Granoble. And they did some calculations on heat and mass balances that we may expect from our process lineup. And this is the basis of the Galores patent that we have recently filed last month. In fact, the number is down at the bottom. So we start here with methane and water going into the reformer. We remove the water that is being formed, and the dry syngas going to the Fischer-Tropsch reactor, where we produce hydrocarbons. We produce some water and Fischer-Tropsch off gas. And our invention is concentrated on this, what we do with this Fischer-Tropsch off gas. So part of it is recycled directly to the Fischer-Tropsch reactor to be recycled over the reactor for producing long-chain hydrocarbons. Another part of the Fischer-Tropsch off gas is sent to the reformer as a fuel for burning, because the reformer reaction, of course, is an endothermic process. So we really need to heat it in order to get the reaction progressing to about 800 degrees. It's typical operating temperature. And we need fuel, and we use this Fischer-Tropsch off gas. Another fraction of the off gas is sent to a gas separator, where we separate out CO2 plus hydrogen. And we send the hydrogen to the burner of the reformer. And the CO2 we use as a oxidizing agent for the reformer process. And we mix it with methane and steam. And then we, of course, have combined mixed reforming of methane. So this is the basis of our process. Then some case study here. We did a calculation, what we consider our base case. Net gas is 210 normal cubic meters per hour, and we produce 91 kilogram of liquid product for a carbon efficiency of 86%. Now this 86% is really important. We are aiming for a high carbon efficiency. And you can compare this with 77% achieved by the Sasol Oryx plant in Qatar. So we achieve much higher carbon efficiency, and that's what we're aiming for with our CO2 recycle. Thermal efficiency is still acceptable at 64. And we can even add in some additional CO2 from an external source. Thereby we can reduce the net gas intake, still produce 90 kilogram of liquid product per hour, and achieve carbon efficiency 92%. Of course, this 92% is calculated on the basis of methane coming in from the flare. So to take that into consideration. But very high carbon efficiency is achieved by this flow scheme. So in summary, our technology is based on proven technologies for SMR and Fischer-Tropsch. We can use our own Fischer-Tropsch catalyst, but the process will also work perfectly fine with other Fischer-Tropsch processes. And for the SMR, we are already working with a third party. So the uniqueness is the CO2 recycled to the reformer where it can be reutilized. And we achieve carbon efficiencies in excess of 86%. We produce low sulfur synthetic crude. And our idea now is to build these modular units off-site for a low fabrication cost, and then to bring them to the flare where they can be started up very easily, and they can be redeployed at other locations once the flare is or the oil well is extinguished. We're looking for partners to do the basic engineering, because that still needs to be done, and to build a demo unit. And to make this basic engineering, we're actually looking for funding and launch customers. So that's where we are at the moment. This is the Galorus GTL. Then if we proceed to the challenges that we see, they are mainly economic. Unfortunately, if you do the business case for this gas to liquids, it doesn't really pay. If I give an example, a small scale gas to liquids plant of, let's say, a small flare, 20 barrels a day oil product. It would cost you in terms of capital about 5 million to have such a module. And the revenues from the oil would only be 400,000 per year based on $60 a barrel. So you would need 12 years before you earn back your original investment. So if you look at the economic business case, it's not going to fly. You can make them somewhat larger, but it's always going to be difficult because the capex will also increase. So other environmental factors need to weigh in. So we have our hope there on legislation and these global gas flare reduction initiatives by the World Bank, that at some moment companies will start to act. And there will be more interest in this technology because it produces a synthetic crude, which they are interested in, which can be put into the existing pipelines. Then if we look at adjacent opportunities, because if you come across a challenge, you always need to look for other things that you might do with your technology. And we've thought about this, that we could utilize additional excess CO2 from carbon capture and convert it into liquid hydrocarbons using our technology. So as I've shown in this calculation example from the University of Ghent, we can convert part of additional CO2 into liquid hydrocarbons with our flow scheme. Another solution that you might think of is that you would take CO2 from carbon capture together with green electricity, and then produce syngas and go over GTL to liquid hydrocarbons. So if I present a simplified flow scheme, here is the flow scheme with the additional CO2 intake. So the reductant here is still the flare gas, and it is just a small modification of our existing flow scheme. We could spice in some additional CO2, but it's limited because in the end you need adequate CO to hydrogen ratio when you go into the Fischer-Tropsch. The other thing which you can do, which might be more interesting for this audience, of course, is if you take captured CO2, you use green electricity, and you start with carbon monoxide production either through reverse water gas shift or from direct electrolysis of CO2 to CO. And you make hydrogen from the green electricity. Then you can produce syngas, you can send to the Fischer-Tropsch, produce liquid hydrocarbons for a tank, and the CO2 and the water which is formed in the Fischer-Tropsch can be recycled over the process, reusing green electricity to produce syngas, and until extinction of the CO2, if that's what you want. So this is something that is a spin-off. It's not our original idea because we were focusing on flares, but it is something that might be interesting for this audience. Looking at our future plans, we are ready to sign agreements with partners to develop products. We're also looking at other technologies with a higher TRL, which can have better economic business case. And we're also looking beyond flare gas, using abundant natural gas to produce blue hydrogen as an interesting energy carrier during this energy transition towards green hydrogen. We think there is certainly a role for blue hydrogen, and with our technology of methane reforming plus water gas shift followed by membrane separation, we could also produce blue hydrogen. So in conclusion, Galores is a Dutch startup company looking at flare gas solutions. We have dedicated founders with backgrounds in chemical engineering and catalysis. We have a good understanding of the global gas flaring situation. We know the competitive playing field and solutions and pitfalls. We have looked at all our competitors, as a matter of fact, and we see what is necessary to have a successful project. And we are thinking about solutions beyond GTL. So with that, I think I come to the final slide. Yeah, thank you very much. And I will be available during the panel discussion later today.
Great. Thank you very much, Carl. Thank you for the presentation. We don't have time for questions now, but again, Carl will be taking part in the panel discussion. And then I don't know if you'll be at the coffee break or not, Carl, but people can always message you, I'm sure, as well.
Sure.
So now I would like to introduce our next speaker, Arne Ketohun. Arne, go ahead and share your presentation. So Dr. Arne Ketohun is co-founder and managing director of Carbon Minds, which is a data analytics company and lifecycle data provider focusing on environmental sustainability in the chemical industry. In his previous position as team leader of a lifecycle assessment team at RWTH Aachen University, he gained extensive experience in environmental assessment of energy-intensive industries, building on his PhD studies at Aachen and the University of California, Santa Barbara. Arne has a background in chemical engineering and economics from his studies at Aachen, Keio University in Tokyo, if I say that correctly, and Maastricht University, as well as from his time as an environmental consultant in Beijing. Arne, go ahead.
Yeah, thank you very much for this kind introduction, and also for the invite to be part of this exciting event. I'm Arne from Carbon Minds. We are a spin-off company of RWTH Aachen University, and we provide life cycle environmental data for chemicals and plastics and consulting in the field of carbon management and transition pathways of the chemical industry towards carbon neutrality. And especially regarding this transition pathways, one of the really important technologies are the ones that we are talking in this about in the seminar. It's carbon capture and utilization and power to X technologies. And this is also, of course, the topic of my talk. The title of my presentation, A Chemical Industry Based on CO2 and Renewable Energy. And in this presentation, we will look into the CO2 abatement potential of CCU in the total global chemical industry. And we also look into the requirements, so in particular, the energy demand. And in order to analyze this, we will, on the one hand, analyze the status quo of the chemical industry. And as you know, today, the chemical industry is almost exclusively based on fossil fuels. About half of it is used as chemical feedstock, so basically what you can touch in the chemicals, and the other half is used to provide the process energy needed. And this is, of course, problematic in terms of climate change, because this use of fossil resources, it causes about 1.5 gigatons of CO2 equivalent emissions per year, only through the production of chemicals. But that's not even it, because those chemicals are afterwards used and they are disposed of, for example, in a waste incineration plant. And this, of course, causes additional emissions. So what we can see here is basically a linear flow from carbon from the ground into the atmosphere. We will analyze this scenario today, or a baseline scenario, in order to compare it to an alternative future for our chemical industry. And in this alternative future, or a scenario for alternative future, the chemical industry will be entirely based on carbon capture and utilization. So in this scenario, we capture CO2 from the air or from industrial point sources, and we use this capture CO2 as a carbon source to produce all the chemicals that we need. And of course, we also require electricity, and we will take this electricity from renewable sources, and we use it either directly to generate the process energy or to provide the process energy, or to produce hydrogen, because hydrogen is of course one of the most important co-reactants of CO2 for many CCU technologies. For this scenario that we would like to analyze, I think we will look into the very concrete details on how this could look in practice. On the one hand, if we need an entire chemical industry which is based on CO2, there's a huge amount of CO2. Where could we get the CO2 from? Secondly, if we get the CO2, how would the chemical industry look like if it were based on CO2 and hydrogen? And finally, how much emissions can we save, and what are the energy requirements? And this is also pretty much the agenda of the next probably remaining 15 minutes. So let's start with the first question. Where can we get the CO2 from? Those are the CO2 sources that we have in Europe, and only the large-scale sources. We have different types of power plants. We have pulp and paper, steel, iron, cement industry, and of course the petrochemical industry. Those are all large-scale CO2 emitters where we could capture CO2. And in addition, of course, there are direct air capture plants, so we could capture the CO2 also directly from air. This means we have quite a choice between our CO2 sources. So the big question is, where should we get the CO2 from? And I would like to answer this question, first of all, from an environmental perspective. So what would be the most beneficial CO2 source if we want to reduce the climate impact as much as possible? And this brings us to a question: what is the carbon footprint of captured CO2 from the different sources? And this caused a lot of confusion, I would say, in the CCU sector over the past year. So let's talk about this quickly. And to understand this, let us do a small thought experiment. Let us imagine we could just draw a line between the natural environment and the man-made environment, so atmosphere versus technosphere. And now imagine I could just magically grab 1 kilogram of CO2 with my hand from the atmosphere, and I could just hold it in my hand. What would be the carbon footprint of this process? It's quite simple. So if I grab it from the atmosphere, if I hold it in my hand, I've just reduced 1 kilogram of CO2 from the atmosphere. So the carbon footprint of this magic process in this case would be -1 kilogram CO2 per kilogram CO2 captured. And if I released it again to the environment, this would then be 0 over the life cycle. The problem is we don't have magic processes. In reality, we need technical processes, so direct air capture in this case. And these technical processes, they always use energy and other impacts. And of course, the provision of this energy this will again cause emissions and also the other inputs. So if we now assume a scenario where we take the electricity from the European grid and heat from natural gas, just as a scenario, it depends a lot on the energy sources, we would generate 0.46 kilogram through the provision of energy for capturing 1 kilogram of CO2. So this reduces the carbon footprint of the captured CO2 in this case to -0.54 kilogram CO2 equivalent that we save by capturing 1 kilogram CO2 and holding it in our hand. But of course, we also have the industrial point sources, and they are already emitting CO2 today. So what we can do here is to go to the exhaust gas and take 1 kilogram of CO2 from there and put it into our CO2 capture plant. So this kilogram will be emitted less. And again, we need energy for capture. So based on this simple thought experiment, we can already give the calculation guideline of how much emissions we save as a consequence of capturing 1 kilogram and holding it in our hand. It would be the -1, that will be emitted less, or that has been taken from the atmosphere. But of course, we need to account for the electricity demand and potentially transportation costs. If you're interested in this paper, we discussed this from a more methodological ISO-like language with authors from many different organizations in the EU and US recently. So I can recommend this paper for further details. But for now, let's just apply this to the sources that I just showed you. We have the results in this graph on the vertical axis, the emissions that we saved per capturing 1 kilogram CO2, on the horizontal axis, the amount that we can capture, and we can see, well, it differs quite a lot among the CO2 sources, like how much we save per kilogram captured. We have the highest saving for example, for ammonia and ethylene oxide, because they produce very highly concentrated CO2 in the exhaust gas. And so thermodynamics lovers among you, they know that, of course, the energy we need for capture, it correlates to the concentration. There's some lower concentrated source, pulp and paper, coal, and also steel and iron, natural gas, power plant, refinery and cement. But of course, in some places, we might not have these large-scale sources that are available, and also in the future, we want to get rid of this. And this means we can still do the direct air capture, which has the advantage you can build it anywhere, and there doesn't need to be transportation in this case. What we did here, we calculated for the European average energy mix. If we do this for the country-specific mix and energy in the different countries, picture mixes up a little bit, but of course, qualitatively, we get to the same results. So we can say, yeah, we save carbon footprints, and there's a lot of CO2 that we can capture, more than 1.4 gigatons here. Let's compare this to the amount of CO2 that is captured. At the moment, of course, we don't capture that much, and we have a lot of sources. So right now, we can really choose from the different sources. This will change a bit. In the paper I showed you, we have scenarios for the future, but where we can still choose a lot, but we can say, yeah, there's definitely a huge choice right now. So why don't we just select the choices that lead to the lowest carbon footprint? And what we can see, well, by capturing CO2 and having it in our processes, first of all, from cradle to gate, so to say, we have a negative carbon footprint at the point of capture. But does this mean that we just need to produce as many CO2-based products, as much in volume as we can to save the climate? The answer is, of course, no, because it's not only the capture that counts. We need to look into the entire life cycle of CO2-based products. We put CO2 in from the beginning. And if you look into an ideal case where electricity has zero carbon footprint and so on, we will still burn the products in many, many cases at the end. So all the CO2 gets released. So even in this ideal case, we reach only carbon neutrality, only in brackets. And if we want to have carbon negative processes of this, is of course also possible, but we need long-term sequestration. This can be done with some mineralization technologies or by carbon capture and storage at the waste incineration plant. So the most common case is not these ideal cases where we have zero carbon electricity. It's more today's case where we have still some carbon in the energy that is used. So in this case, the carbon footprint is not neutral. It's more it's more a bit higher than zero, but what we can say, well, in many cases, it's much lower compared to the fossil-based equivalent. So by replacing the current fossil-based processes, this is how we reduce carbon. So for many, many CCU technologies, it's not that we put the CO2 in the product because it was burned in the end. The emission reductions, they come from the substitution of something that is more polluting than our new processes. Yeah, and this is important. This is why I put some exclamation marks here. So let's look into this potential substitution in the chemical industry. How would the industry look like if it were entirely based on CO2 compared to the industry today? Today, the chemical industry is built in a tree-like structure. We have the fossil resources that are based converted into feedstocks, which are used for the production of platform chemicals, like olefins, aromatics, which are again the platform for the production of all these thousands of different chemicals that we have today. What is important is it's a super interdependent production network. So plants use co-products from other plants. We have energy integration. So if we want to analyze the mitigation potential of CO2 utilization, we can't just do LCAs, life cycle assessments for individual products and sum up the results. No, we won't capture these interdependencies. We need a comprehensive model of the chemical industry that can catch all these interactions. And this is what we built in another study, which I would like to show you here. And we built it for this part of the chemical industry down here for the production of large volume chemicals. And there's a list of the chemicals that we considered in the upper right corner. What is interesting about these chemicals is that even though we have thousands of different chemicals produced in the chemical industry, only 20 large volume chemicals, the ones that we see here, they account for about 75% of the cradle to gate emissions of the global chemical industry. So this is why we chose them as a scope of our assessment, and we compare the best available fossil waste to produce them with the corresponding CCU processes. We did this by first analyzing all the production pathways, and of course, for the 20 chemicals, we have many more production steps, about 160. In this case, we modeled process flow sheets for every single production step. We extracted mass and energy balances and the direct greenhouse gas emissions. And we used the data to build a full bottom-up model of the chemical industry. So basically a model where we can track physical flows from the oil to the product, in our case, those 20 flows, and can also track the emissions. The nice thing is, once you have such a model, you can start playing with this. And what we did, we transferred it into an optimization framework where we minimize the greenhouse gas emissions for the provision of the final demand of those 20 basic chemicals for the year 2030. Why minimizing emissions? Well, if we minimize the emissions based on CCU, compare it to the baseline scenario, we calculate the maximum potential of CCU. And this is what we did. So let's look into the baseline scenario, the conventional scenario first. So first of all, we put in the final demand in our model. We allowed the model to use only the resources that are already used today. And we run the model and get based on this optimization, our structure of the chemical industry. And here again, fossil resources go into platform chemicals, which are the basis of all the other chemicals. So what we see here is basically a more detailed representation of this part of the chemical industry down here. And also the emissions are very similar if we compare to different standard studies. And this was important because for us, it's of course just the validation step of our model. Now that we know that the model works, we can go a step further and also allow the model to use CO2 and hydrogen from water electrolysis as feedstocks. And we do this in two scenarios. First of all, a high TL scenario where we only allow CCU technologies that produce one of our 20 large volume chemicals with processes which are at a very high technology readiness level. In our case, almost mature plant level pilot plants available. This was the case for methanol and methane here. So we again put the final demand in our model, but this time we allow the model to use CO2 and hydrogen. We implemented the CO2-based production technologies for methanol and methane, and we let the model run again. And what we obtained is a completely new structure of the chemical industry. And what you see here is a scenario how the chemical industry could look like if it were entirely based on CO2 and hydrogen. This picture has two messages, a good one and a bad one. The bad one first, we see there's a lot of co-production of water for the production of methanol and also methane, and also for the methanol to olefin processes, which we need to come from methanol to the olefins and the aromatics. And co-production of water means that the plant capacities need to get higher, so plants get bigger, more expensive, and it's an indicator for less efficiency. But what we can also see is this part of the industry. It hasn't changed at all compared to the previous scenario, because we use CO2 and hydrogen to get to the olefins and aromatics, the platform chemicals. And we know those are already today the platform to produce all the other chemicals. And this is why everything in this part stays the same in this scenario, which would be important to keep the infrastructure and reduce investment costs needed. But of course, in CCU, it's a new discipline that got a lot of attention over the last decade. And there are many technologies which are not at high TRLs, which are at early research and development stages. For our 20 chemicals, we included some more of those. Those are direct routes from CO2 and hydrogen to ethylene, propylene, BTX, and some other chemicals. And now we included those also in the model and let it run again. So again, CO2 and hydrogen can be used, and we get a new feasible structure of a chemical industry based on CO2 and hydrogen. Here already see less water production seems to have a higher efficiency. We'll analyze this further in a bit, but we can also see through the direct route, we replace very much of the existing infrastructure. So this would be, most likely connected to much larger investment costs. But from a technical point of view, this is technically feasible. So by this, I think we have learned how the industry at least could look like if it were based on CO2 and hydrogen. So let's get the last step and analyze how many emissions we could save by this. And to do this, I brought this diagram. On the vertical axis, we have the cradle to grave greenhouse gas emissions of the global chemical industry. And on the horizontal axis, we have the carbon footprint of the electricity that we use. You remember we produced hydrogen from electricity, so electricity carbon footprint seem to matter here. This is the result for the conventional scenario, about 4.3 gigaton of CO2 equivalent emissions a year, about half of it through the production, a bit higher than today because the demand will increase, the other half due to waste incineration of these chemicals at the end of the life. And this is the result for the high TR scenario. And if we compare those, we can first of all see, whoa, there's a huge climate impact reduction potential. 3.4 gigatons per year, and we're getting close to zero for the entire industry. The remaining gaps, part of it is, for example, non-CO2 emissions with a higher global warming potential. If we look into the low tier scenario, the impact reduction is even slightly higher. You see ranges for each scenario. This is because we have the different CO2 sources, so it's the upper and lower range depending on what CO2 source you choose. But what is much more important here is what we can see, well, if we want to achieve these substantial reductions, we need extremely clean electricity. And this electricity needs to be even cleaner compared to some of the very clean grid mixers that we have today, like Austria, Belgium, and Switzerland. You wouldn't have the huge reductions there. We really need renewable energy, like wind, solar PV, and we will need a lot of it. So this seems to be difficult, at least from a first analysis. So how difficult is it? How much electricity would we need? To understand this, I brought a different graph. Again, vertical axis, climate impact of the chemical industry, but now on the horizontal axis, we have the amount of renewable or in general of electricity that we can deliver to the chemical industry, in addition to what is used in the business as usual scenario. We have the results for the business as usual, the conventional scenario, which doesn't need additional electricity. And here we see the results for the low TRL scenarios. I.e. the climate impact, depending on the amount of electricity available and the carbon footprint of the electricity that is used. And those are the small colorful numbers on the side. To get back to the question, how much electricity would we need? Well, in this scenario, we would need 18.1 petawatt hours. What does it mean? As a comparison, I brought the renewable energy target from the Sustainable Development scenario of the IEA for 2030. And we can see this target is for all the sectors together. Only the chemical industry alone would need a bit more electricity even than all the others together in this scenario. And I know there are some criticisms that the scenario is very conservative, but I think we can agree that those are very huge amounts of renewable electricity. And if we have only the high TR scenario, it will be even more. The good news is, well, we see there's a difference in slope here in the scenario, so meaning the greenhouse gas reductions per kilowatt hour of renewable energy differ. So if we don't go for the full implementation, we can at least use those technologies which mitigate climate change most efficiently based on the kilowatt hours needed. But again, if we only go for 10%, 20%, 30% implementation, we're still talking about very huge amount of electricity needed. So as a society, we need to decide if we want to use our precious and most importantly limited renewable energy, currently limited renewable energy, for CCU in the chemical industry, or are there more efficient uses as long as we don't have enough renewable electricity? And to answer this question, I put some lines for comparison here. Those are the emissions reductions that you could achieve if you didn't use electricity for the chemical industry, but for electric boiler to substitute natural gas boiler or heat pumps, or for e-mobility to substitute diesel or gasoline cars. Sorry, I need to drink a bit. And what we can see here is that those other large-scale users, they reduce the climate impact more per kilowatt hours. So meaning, as long as we don't have enough renewable electricity in the next few years, we should make sure that we don't take it away from more efficient users. Or the other way around, the potential contribution to climate change mitigation of CCU is where and when more efficient users are not available. So we don't steal it from them basically, so that we can use otherwise unused renewable energy resources. Sounds a bit theoretical for now, but let's look into where we have renewable electricity or energy resources in general. And this is the size of the bubbles that you see here. It's super small in Europe, for example. And the huge resource availability, this is, for example, in Australia, it's in Africa, it's in South America. And if you've ever been to the desert of Australia, there are no electric cars and no heat demands. So if we can make it possible to use this otherwise unused renewable energy, transform it into CO2-based energy vectors or chemicals, which can be further processed in the current industry locations right now, then we would enable a trade of renewable energy, a global trade via chips, and we could really use the huge potential of CCU in the chemical industry here. And we are further investigating this scenario right now, and I believe that this is something very interesting to look at. So in terms of conclusions, we have seen CCU has a huge climate impact reduction potential, but it also requires quite a lot of electricity. When we implement it over the next years, as long as we don't have enough renewable electricity, we need to make sure that we use this renewable electricity most efficiently. And here CCU is less efficient compared to several power to heat and e-mobility applications. So a huge potential would be when these other options are satisfied and where these other options are not available. And here CCU can really make a huge contribution to climate change mitigation. So with this, I would like to thank you for your attention and look forward to the discussion session later.
Great, thank you very much. Very, very interesting presentation. So we'll skip questions for now and we'll reserve them for the panel discussion. Please feel free to put any questions you have in the chats. So with that, I'd like to introduce our final speaker, Jeroen van Woerden. Jeroen, go ahead and share your screen. So Jeroen is an internationally oriented general manager who leads organizations to improved operational and financial results. He has experience in leading several industrial organizations in Germany, France, and the Netherlands, and is currently the managing director at The Gate, which is a platform for tech startups involving business developers from Brainport Development and the Eindhoven University of Technology. Jeroen was the quartermaster at the inception of the Field Lab Industrial Electrification, which he will present now, and continues as a strategic advisor. So Jeroen, go ahead.
Thank you, Erin. Can you see my screen?
Yes, we do. Great.
Very good. Yes, thank you very much. And thank you for the opportunity to present the Field Lab. In my role as quartermaster for the Field Lab, we started the Field Lab Industrial Electrification. And it's very well connected to the former subject of the former speaker, because we speak about the application of electrification in the industry. What I want to tell today to you is especially the perspective from the user, from the industry, how to transform their businesses towards renewable energy. I assume there is enough green electricity, because that's of course one of the critical questions just raised. And we as a Field Lab have the job to help this this industry in making this change. The mission is clear in Rotterdam. We have a climate agreement, a national one and a local one, and we agreed that we will strongly reduce the CO2. And I think that's a good starting point because everybody's convinced that it has to be done. The ideas are there, the technology is in development, and today we discuss a lot on that. But the key question for the industry is how to get the job done while the industry continues production, while we face day-to-day practices and challenges, and at the same time have to do this huge transition and secure also the future economical situation of the industry. At this moment on the North Sea, there is a huge transition as well going on to secure the supply of green energy. So the focus is to help the Rotterdam industry in making this transition. The climate agreement was strongly supported by a huge group of companies who said, okay, we have to do this. But at the same time, this group of companies said, if we implement in the running business the electrification, we will face a number of challenges. One of the challenges is continuation, safety. I come back on that later. The technology implementation. And of course, there is limited space to learn in the running industry. So that was the reason why this group in Rotterdam said it should be good if we have a place where we can do tests, where we can industrialize, and where we can bring the technology from a lab skill, from a development skill, up toward an industrial skill and fully implement that. And there was a clear need for experimentation. We needed to invite innovative players, technology developers who have solutions like we see today. But we have to do small tests, small scale tests, but still on an industrial scale to test if it is fitting into the industry. And the last thing was very important, also driven by the government, is maximize the learning capacity. And next to that, the lobbying effect was just said. If there is not sufficient green electricity, the transition will not work. This is all done next to the other transitions that are going on in Rotterdam, which is the hydrogen transition, which is going on, the feedstock transition in the same industry. So the industry has a huge challenge in front of it. With the field lab, we focus on the electrification. And this is our statement that we send around to everybody. We really want to unite players from around the world to bring them together to Rotterdam and to help this energy transition in Rotterdam. And for that reason, the Port of Rotterdam Innovation Quarter, which is the development company of South Holland, TNO, Delta Links, the memberships club of industrial companies of the Association of Industrial Companies in Rotterdam, as well the FMA, which is the Association of Manufacturers for High Tech in the Netherlands, supported by the government, European Union and local governments, decided to start this field lab. And I will tell you in this story what we do with the field lab and how we support the industry, as well support the technology providers. The key challenge that we have is we have a technology on lab scale with lower TRLs. It's well developed, the ideas are great, but at the same time, the industry is running. There is a very strong demand on this industry in continuation. There is a high pressure on cost control, but there is also a high pressure on safety control and management of change. And it's a huge step to make this step from pilot towards an industrial application while continuing the business. Some people may say, why don't you focus on the greenfield solutions? That is a possibility. On Maasvlakte, that's close to the North Sea, that's possible if we build a third one. But if you look back in history, the biggest part of the Rotterdam industry at this moment was still existing 20, 40 years ago. And it's reinventing and reinventing and reinventing. And with that, it extends lifetime and it becomes more and more innovative. That means that it's a fair assumption that in 20 years from now, big part of that industry will still exist. And that means that if we want to achieve our carbon reduction objectives, we have to change this existing industry. And that is the objective of the field lab. Why did we choose for a field lab? There are many technologies available for CO2 reduction, and a number of them we discussed today. Actually, in general, you can state there is no best solution. There is perhaps a proper fit with the current situation, but that means that you have to check if the technology available is fitting in the situation of the industry. And the industry has to search what are the technologies available, and they have to make their choices. And to help them in making the right choices, the field lab has the objective to do a first selection and validation of available technologies and share that learnings with the industry. It's a very public function, so we share broadly what are our results. We want to create strategic options for the industry. The industry has to combine this challenge not only with the carbon reduction challenge, but at the same time, as I just said, they reinvented themselves all the time. New products are developed. So that means that at the same moment, they continue with innovation, luckily, because they improve their products. They continue with safety improvements. They continue with efficiency improvements, and they continue with their maintenance programs. And that means that they have to make options, what kind of technologies they reduce for carbon reduction, for electrification, and what is the right timing for that. Very important is that most of the industries have their hard stops for the overhauls. That means that they do the planning in 2021 for 2025, 2026 for the overhaul. So that means at this moment they have to know already some options which they could implement in 2025. We have at this moment some real life cases where we are working on this kind of situations. The government, Dutch government as well, European government are very much supporting the energy transition. Huge funds are available. But subsidies are sometimes difficult to get and to achieve. You have to fulfill the requirements and the conditions for that. And we see that too many companies don't use the options. And that is, at the same time, if they discuss opportunities for electrification, one of the challenges is that they don't have proper business cases. And this is where subsidies can help a lot. They can strengthen business cases. And the last one I talked about the risks. We have to de-risk the implementation of the technology. It's not that the companies are not brave, but there is an extreme limited acceptance from society, from accidents in the industry. That means that there is a strict control of the industry. More than any other industry. We see that quite often when suppliers are coming. The suppliers are coming from the make industry, which has its own challenges, but on safety, they step into a new world if they go into the process industry. The process industry has a very strong demand of safety, and that means that everything what we implement has to go through a management of change process. And if it is a new innovation, sometimes that's not an easy step. And that's the reason why we also want to support those companies. And this is what we really want to facilitate. On one hand, we have the equipment industry offering all kinds of solutions, new ideas, offering the different options. And there we have startups, small companies, and established technology firms. And we need all three of them. The new entrants offer very innovative solutions, but at the same time, not proven. Established firms have a strong relation with the process industry, but at the same time, also they have to renew their business model. And at the same time, the process industry is the end user of the technology. The efficiency of the assets is extremely efficient, and in the process industry, price pressure from the market is huge. And it's the backbone of Rotterdam. And what we really want to facilitate is the exchange of know-how between, on one hand, the solution offerer, as well, at the other hand, the end user. But we place the end user central in this discussion. In this picture, I try to show you what we do. On one hand, we have the technology, battery solutions, network, a lot of know-how, and of course, electrical solutions. But there's another aspect which is important. I already talked about money and the financials, but regulations is also a very important thing. As we said, the process industry is a very heavily regulated industry. That means that regulations are in most cases built on history, and if you implement new technology, that means that sometimes it really conflicts with existing regulations. I will give a few examples. For example, now in the electrification, we see that the demand for power supply is much higher than it was in the past. To do your maintenance, you need already different skills, and also you have to fulfill different regulations, because the regulations of the past were built on a history where the power supply to industry was high but limited, and in the new situation they triple or 10, sometimes they increase 10 times their electricity demand. And that is the same with permits. So it's technology in the combination with everything what is in the environment around. And this is also where the consortium is so important, because we have with Innovation Quarter the governmental investment company on board who is a specialist in financing. With FME, we have the supply of technology on board, and they are key in innovative solutions. Port of Rotterdam facilitates the Port of Rotterdam, and actually is the key, has the key interest to reduce this carbon output, because with that they secure the future of Rotterdam. TNO very strongly in developing technologies, and Delta Links, they represent the owners of the assets. And with that, we combined actually all the groups in this joint field lab that we set up. In options, there are multiple options that we support at this moment. Based on the developments with green electrons, as I said, a lot of activities at this moment on the North Sea in supply of sustainable electricity. At the same time, also a huge shift going on in feedstock, and a lot of solutions coming up, not yet implemented, but in the next coming years, this will change dramatically fast with green molecules. And we work together with the industry on the integration of those equipments. And with that, we have solutions for power chemical, power to heat, and depending on the challenge that the industry has, we are working now on projects with them and try to speed up and accelerate their projects. How do we do that? The field lab has actually three functions we are building, and the first one is opened last January. We have a solution center where we give advice, and I will tell a little bit more in a minute, and we support the companies. And actually it's an administrative center where especially the know-how part, the financing part is a very important backbone. At this moment, we are building one of the most important steps of the field lab. We are creating a pilot and test location. In this test location, and that could be one or two locations in Rotterdam, depending on the applications that we're gonna develop, we want to facilitate that we can do tests, experiments, and pilots projects in a location in the TRL level 4 to 6. It's still pilots, but in an industrial scale. This must be also a demo location for new technologies. That means that solution providers who work together with us, they build their technologies there. We can test them in an industrial environment, but they have the opportunity to show to new customers. And that's not only in Rotterdam focus, but it can also be customers from them from all over the world come over to this location, and they can show their new technologies. And for Rotterdam, even more important, the industry can take a look to the technologies. And one of the things is they can already start to train the operators to work with those new technologies. They can do checks with and tests with technologies, and they can build their implementation plans and feed their choices with these technologies. And that means that we build up the know-how in this industrial setting. The last step that we want to do with the field lab is build demo locations. And actually, when we talk about demo locations, this is not anymore purely field lab activity. This is more process industry activity. These are the partners, the companies who, together with the field lab, develop in their plans an TRL 6 to 8 demonstration project. And it's a project in the last phase of development. And they do that to check and to implement. For that, they will get support. And this is one of the demands that the government has in the Netherlands. They are more than willing to subsidize companies. But one of the returns that they want to see is that the learnings of those technologies are shared with other companies. And that's the nice thing that we do with the field lab, because in most cases, electrification is not on the competitive edge of the companies. We don't share their typical processing things. We don't share their chemical formulas and this kind of things. We are really working on the electrification, which is mostly in the periphery of their core processes. So a plastic producer, the electrification supports this process, and that makes it possible to share learnings around the electrification. This is a shift in mindset, because in the past, chemical industries by definition were quite closed, and actually, so we ask companies to open, and in return they get support. And that means that we have knowledge exchange on risk mitigation, implementation, but we can also influence with this legislation and regulation, which is a benefit for the whole industry. The Solution Center is already started. That is now in the middle of Rotterdam. We have, on a very nice location in the harbor, we have started a Solution Center close to the education institutes. And in the Solution Center, companies can and suppliers of technologies can get support in know-how. We help them with feasibility studies. We do business case developments with them. And also the governments are asking feedback from us from studies, what they have to change to improve the conditions for this whole transition. Especially together with TNO and FME, we drive also our innovation plans here, and we facilitate the cooperation with other technology institutes, and also here the exchange of information, but also the building test cases for the future. And the next step that we will do is we will foster the collaboration between the companies, so that companies quickly can exchange know-how, learning aspects, and that they can get support for further research. Timing-wise, as I said, the field lab is started in the Solution Center beginning of this year. That was also the moment that the quartermaster phase was at the end. The central hub, we hope to open them and to announce that in the second part of this year. And when I say hope, is because we are extremely hardworking at this moment to make it possible. So the expectation is that it is at the end of 2021, but everybody knows that in the current COVID times, we have a lot of uncertainties to manage. So in 1 year time from now, you can visit the central hub location. And the field lab demonstrations, we expect to have them from 23 onwards. Yeah, why this testing environment? Actually, the most important sentence is on the bottom. The best technology doesn't exist. Every company needs its own solution. We speak too often with companies who said, oh, my technology is a no-brainer. And then I always ask them, how does it fit with your customer? Do you really know what your customer needs? And in most cases, the customer has a more balanced question. He needs to change and reduce the CO2 output, but that in combination, for example, with a maintenance overhaul. And with that, he has to balance his ambitions. So we have multiple options that we discuss now with them. And with that, we give the companies the options from backup e-boilers, multi-fuel burners, which is not an electrification solution, but it clearly came up when we were working on furnaces that it was too early to make the step to electrical heated furnaces. So we took an in-between step with the multi-fuel burner. There's a great interest in the industry. Industrial heat pump integration. Now you can read all the examples that we have, but at this moment we are also discussing with a number of companies the implementation of synthetic fuel production and distribution. With that, we create at this moment the roadmap of solutions on the left side. And sorry if you ask what is CO2, that means company 2, company 3, company 1, because I cannot disclose the companies we work with. But we have an ideation phase at this moment relatively well filled with all kinds of companies who have interest. And in most cases, we are working with them together on business plans and looking if we can make a feasibility. In project development, we have a number of projects at this moment around power to heat examples in preheating and e-boilers, but also power to chemicals, e-kerosines, e-methanols are very important. And in concrete projects at this moment, we are doing, as I said, multi-fuel burners, one of the most important projects which we are running, heat pump projects. And at the same time, on behalf of the government, we do a number of studies for carbon synfuels and hydrogen carriers so that the government can set the right conditions. Why is it so important? And you hear me not talking too much about technology because they're much better specialists, but implementing all those technologies, there's one thing very important, and I know some people said it's a choice between environment and economy. We believe it's both. In the end of the day, we drive this whole industrial change because we want to have a strong economical force in Europe, which helps to develop the society further, and of course in a clean way. So that means that it's extremely important that we maintain the competitive position of the industry during the implementation. That means that implementations with breakdowns or stop of a plant are in most cases disastrous for the company, especially if the breakdown is not predicted and uncontrolled. Secure process control, as I said, a lot of regulations is together with the next point, safety. We implement in existing processes all kinds of changes. And there is a very strong reluctance of the same society who is asking for the improvement of the environment for accidents. There is zero tolerance. That means that in Rotterdam, we have a culture of zero incidents, and we have to maintain that. And companies have a big worry on this point, and rightfully so. So that means that we have to create that environment where we can learn, where we can change, while maintaining safety. Regulations. What we see in most of the cases that we run now is that regulations are a limitation because the regulations are designed for the past, for solutions of yesterday. And we are implementing solutions of tomorrow, and we are developing solutions of tomorrow. So one of the things that we also have as a rule is giving back feedback to the government on what is needed to change in regulations. One of them is, for example, the power connections at this moment with the grid. In the current situation, even if we install things like e-boilers, the demand for power is already so high that we cannot work with the local electrical supply companies. It has to be with the national ones. Not because the regional ones have to say, I'm not willing to do that. No, the law forbids it. At the moment that the power demand is so high, it has to go via TenneT. And the last one, very important, is the human capital agenda. There was already an engineering and craftsman capacity challenge in the region. Technology and students who study technology, they become more and more scarce. But at the same time, at this moment, we are also changing their skills. If we electrify, we need more and more electrical people. And electricity is one of the most regulated jobs. For every step in the electrical engineering process, you need a certain kind of skills and testing and permits. And that's different than on the mechanical side, where you have a little bit more freedom to operate. That means that the demand on the right craftsmen and the right engineering is increasing, while we already had a chance that we had less youngsters who were interested in that. So re-education of people on the labor market is an extremely important thing. And last but not least, the maintenance skills are changing. Sometimes it becomes more now not simple is the wrong word, but a change in a positive direction. But at the same time, that means that you have to build up skills for this electrification. So the human capital agenda is a very important step of our approach. Now, this is my last slide. Why do we do this? We need the cooperation is key. We all recognize the need for energy transition. It's recognized by the government and industrial players, but it's also recognized that it is a huge challenge. It's unsure, and it has a lot of unsolved technical solutions, but also economical questions. And we have to learn faster. And with that, we have to share the unique know-how to support, and we have to create that learning environment, not only around people, but also around companies who quickly share. And that's more than a benchmark visit. That's really sharing the in-depth know-how, which for most process companies was in the past limited to their peer company in the same group of companies, where now we ask them really to share also with other companies. Cooperation with different players and entities in the value chains, that helps. So that means that energy suppliers have an important role in that. And with that, and that is what we want to do, is we want to secure and strengthen the competitiveness of the industry. So we want to have a cleaner industry who is better competitive in the future, and that in 2005 we have a CO2 neutral industry who is really leading in the world. And with that, I think it's a clear example of connecting on one side technology and sectors, and in our case, the sector is the process industry. And I'm more than willing to answer the questions during the day.
Great, thank you very much, Jeroen. Good, so I'm going to go ahead and turn it over to the panel session. So if you have any questions for any of the keynote speakers, please go ahead and put your questions into the Zoom chat or the Whova chat. Jeroen, if you can stop sharing your screen, great. So I'll invite all the panel speakers to please start your video. Great, I see you all. So as the questions come in from the audience, I'm just gonna kick off some discussion with a couple very broad, open-ended questions. And feel free to answer as you like. So the first one, so in your opinion, what is the biggest barrier preventing the deployment of Power-to-X or different sustainable technologies today? And please answer as you like.
If I may ask, I sometimes challenge people, and in this group, it's perhaps a dangerous statement that I'm going to do, but in most cases I say, on short-term, technology is there. There is a lot of technology. There are a lot of technology suppliers with great ideas. It's really the implementation into the industry, the willingness, and to make proper business cases on that and to overcome that, what I just said. So the bigger barrier at this moment on short term is implementation power in existing industry and building good business cases. On the longer term, for sure, technology again, because we have to continue with development.
Maybe to add to this, it's also the willingness to walk along the learning curves. I mean, we have a quite unfair competition. We have fossil-based technologies that we've been developing for decades, and now those new technologies that need to compete in minute one. So I think we need quite a lot of support, and projects here like this who are de-risked through public funding are really important. And I think we need the funding and the willingness to start it and to learn, improving those processes over time, I guess.
Great. Any other comments on that one? And this came in from the audience, Arne, during your presentation. What was your opinion regarding the use of biomass? But any of the speakers, please feel free to comment.
That's a very good question, especially after I presented such a one-sided scenario where we only went for CCU and not biomass and not chemical recycling. Maybe to start with a more general statement, I believe that the future will see a mix of all these technologies. The technologies have advantages and disadvantages, and we can't say this in general, biomass is better than CO2 utilization, because this comes down to the options that we have for every single process that we have. For example, some polymers you can't recycle because of the additivation, and here biomass utilization and CO2 may be more advantageous. But in some other cases, if we can put plastic residues in the steam cracker and conserve the energy, which is already in the plastic, this can have huge advantages. I think for biomass utilization, the availability of biomass is a huge problem. We once contacted a ministry in Germany to ask if they have numbers, and he was joking, yeah, there's no biomass availability, which is of course was a joke in this case, but it's something true. If we talk about like providing feedstock on a very large scale to the chemical industry, their biomass is certainly limited through the availability and the competition with food, for example.
Yeah, if I may add, I think biomass, I agree with Arne, first of all. We will see a combination of different solutions. But I see biomass already being used, of course, in refineries where there is co-processing of certain animal fat, oil. What I also see now is that, of course, there is separation of municipal waste to take out the organics, to gasify it, and then go into sustainable fuels to make hydrocarbons out of it again. So I think there is certainly a space, and I see some of these projects already reaching commercial use.
Mm-hmm. Great, thank you. So let me go to my next question. What changes are needed to make either power to X or the CO2 utilization or alternative fuels happen in industry?
Anne gave already a good remark, and when he said that we compete with new technologies, with existing technologies who are developed for long term. So the most important thing, and that's the reason why I said around the technology is so important, is that we create business cases, because for most companies they are challenged just by economical sakes, even if they are already convinced that the sustainable change is necessary. And most CEOs don't say that just for window dressing, they really believe it. But at the same time, they live in a world where the economical drivers are also still valid. So one of the most important things is to create proper business cases, and for that subsidies are extremely important. Support of the European government and the national governments is that you get business cases ready, and that you're going to make the situation that you're going to test those situations, because at that moment you start the learning curve, you start to develop, and you start to further improve the technologies, because we will make mistakes in the beginning. So really make it happen and get proper business cases.
Great.
Another factor which would also be very helpful here is to have policy instruments that incentivize the new technologies by making them more price competitive. So what we see right now is a fast growing price in the EU ETS, but for CO2 utilization, it helps making the competitor, the fossil-based technologies, less competitive. So they get closer to each other, but at the same time, the CO2 that you capture from a large-scale installation within the boundaries of the EU ETS, it still counts as emitted. So you don't save emission certificates by capturing CO2. And there are good reasons for this, because the CO2 would be, basically, there would be a loophole out of the system boundaries of the ETS. But at the same time, an efficient carbon pricing where life cycle emissions are priced. Maybe not always directly through life cycle assessment, which might be complicated. And this should be the goal.
Great, thank you very much. And it's good, the project, the E2C project is working a lot on these business cases also that Jeroen mentioned. So I hope everybody will stick around for the second part of the event to also hear about those developments. Okay, then the next question, what is the biggest myth around power to X or sustainable technologies, in your opinion? bit of a tough one.
Yeah, I was waiting that Carl wanted to say something. But now for me, the biggest miss is, and that is, you asked the question on the biomass, and I did not react on that one because the other two did. But for me, the biggest miss is that sometimes we believe in technologies as if it is a religion. And that's the reason why I said there is no best option. We have to check multiple options. And in some cases, one option fits perfectly, or we prove it doesn't fit. Also, that learning we have to go through. And I see too many discussion in literature. What is the best solution? Is it hydrogen? Is it this? Is it that? And in most cases, it's dedicated to the situation. And I'm quite sure that the things that we design today, in 2030, we will have a different view. So the miss for me is if people really stick into solutions where they say, oh, this is the best solution. Yeah, that's the reason why I stated there is no best solution. There is a good fit, and that fit will develop.
Any other comments on that one, on the myths around these technologies?
I really like the answer. I think maybe to add on this, we shouldn't mix up tools with goals. For example, a circular economy is more a tool creating more circular carbon flows, but our goal should be to solve the climate and other environmental problems. And sometimes when I see I don't know, package labeling where it says the amount of recycled content. Well, it's nice, but why do we want to recycle content? Like the avoided, okay, for plastic, we have the plastic in the seas, which is one point, but from a climate impact, we want to see how much emissions do we save. And sometimes you can create CO2-based products and make it even worse situation if you do it badly. So here, doing CO2-based products as an example is not a goal, it's a tool. So let's compare technologies based on their outcome and their goal achievement instead of whether they are recycling or biomass or CO2.
Great, thank you. Good. So let me ask a question coming in from the audience. Are there any ideas how could emerging markets finance costly, expensive technologies, such as power to X, such as CO2 utilization, such as gas flaring, or GTL?
Well, I think they will need some help with the financing, or if they have the resources, the natural resources, of course, they could be utilized. But I think in general, they will need a lot of financial help and also with the technology. But then it's a global issue that we need to address. So I think we should find a solution for that.
Yeah, I agree, and I give perhaps more an ideal answer for myself than, and I quite strongly believe that people in the field lab will believe it, but we never discussed it. I think COVID, which is not a climate issue, but it's also a global issue, showed that we live on a very small world where we influence each other. And that's the same with the climate change. So in the end, there is not other option that to do it together, and that means that we have to support them. On the other hand, if I look to the nice picture of Arne, where all the sources are, and we have to really to use the sources available in other parts of the world, and we have to pay a fair price for that. And I know that is a challenge with business cases, which I advocate by myself, but then we have to find ways to really value properly the contribution that people give. And I know this will not be on short term, but it is absolutely necessary, and COVID proved that we can be overwhelmed by a global problem.
Yeah, good point.
And maybe renewable energy could be the new oil of the future. So the research-rich countries are in different locations. And I think we should also see that it's an imperative to make this happen, because if you see companies reporting on their Scope 3 emissions, meaning their supply chain emissions, they're trying to reduce the emissions along their supply chain. And if we have much worse energy mixes, for example, in developing economies, this means that companies here, for example, they will find it harder to buy from there, because this would increase their Scope 3 emissions. So it could even turn out to be quite a strong disadvantage. And companies who compensate their Scope 3 emissions through offsetting, they would even pay on top of this to buy from these regions. So I think it's very important to see this transition in the different parts of the world and not to create additional barriers for development through this.
Great, thank you. And I just read this comment that came in from the same person who asked the question, I believe. Just says, so yeah, it is a big challenge. There's a big potential in Latin America, for example, but other concerns shadow the potential of technologies. International investors are needed, definitely.
I think one of the important things that we have, and that's a big discussion, how do we value intangible assets? And that is in the climate change, a very important thing. And now here we need also breakthroughs, because as long as we have only the tangible assets which we value, we are in the current business models, we don't value in the proper way the solutions that are possible. And that's also a change in mindset.
Mm-hmm. Yeah. Good. So let me round off with one more question before we get to the coffee break. It says, if we would not have the climate change argument, would there be an incentive or a reason to use CO2 to make chemicals?
Yeah, I really like this question. And it's also a problem, and I also contribute to this. We often talk about climate change and we often forget that climate change is only one of many problems for the environment, including biodiversity, water, and so on. So are there other incentives? Of course there are. We have resource depletion. This is the most directly affected one. It will create potentially safer supply chains. So if you're not bound to individual resource suppliers because you build a system which is based on CO2 and renewable energy, which is available in many more places in this world, and it doesn't depend on individual actors, so it could create safer supply chains. And there are also CO2-based products where you can very directly affect other environmental impacts. For example, we published a paper on fuel additives based on OME, and we showed that for diesel engines, maybe you remember the VW scandal with NOx and the particles, that this additive could reduce these other impacts and the particles and the NOx to a level that you wouldn't even need an exhaust gas treatment anymore. And this was an example of a CO2-based product which made this happen. Another example could be a CO2-based polyurethane, where you could adapt some of the product properties in a very favorable way. For example, in the field of dampers and so on, where you really create better products based on this.
I think another reason is because CO2 is actually the outcome of a lot of problems that we create as mankind. We have overpopulation, so we have scarcity in ground. We take away the resources from areas where people live, and we have proof points enough what we did. And of course, you can link it to CO2, but look also to the environments that we created in that areas. We have a pollution problem. We create quite some waste. So there is this very strong reason, apart from the CO2 reduction, to have that circular economy in place, because we have the sources and we have to reuse the sources. And the growth in population makes that we will go quickly to 10 billion people. So even if the planet had no problems with our CO2 reduction, we had other challenges. And I think now CO2 reduction is a little bit more or less chosen as the carrier to pinpoint everybody in the right direction. I think rightfully so. At the end of the day, it's a sum of all kind of other problems that we have.
And that would be interesting to hear from Carl. Do you think that companies would use your kind of processes, GTL, for the flare gas if it wasn't for climate change? Are there other incentives?
I'm afraid not, because as we have seen over the last decades, they don't worry too much about the CO2 emissions. They are after the oil. The gas is a problem for them. There is no takeaway. The simple thing for them is to burn it. And there is absolutely no interest to do anything. So we really pin our hopes on the worries about the climate. And as the previous speaker said, that we need to go to a circular economy and minimize those CO2 emissions. And oil companies have said that they will do their best to decarbonize their supply chain. Of course, still they produce the oil and bring it to the consumer, and eventually it will be burned, and CO2 from the combustion will come into the atmosphere. But at least this avoidable CO2 at the oil well without any economic benefit, hopefully that will stop rather soon.
Okay.
And also, if I may add, without running out of time, I think we also have a quite an advantaged position here in the rich West, and we need to realize that many countries, they have actually energy poverty, and we can talk about a nice electrification of our economy, but these people are happy if they find a piece of wood to burn their evening dinner. And these inequalities also will need to be addressed, and hopefully we can do something with that new technologies that we can find.
Yeah, that's a great point. Thank you.
Maybe this
Good.
could even help there if we can create products in these areas to create an additional revenue that could support for example, the electrification in these areas. So I think this is a really exciting field where we should work on much more.
I liked your graph with the big circles in those countries.
Oh,
yes.
Yeah. Oh yeah.
Yeah, indeed. Very good.
Mhm. Yes, definitely. Good. Well, with that, I would like to wrap up the panel session. Thank you all very much for your presentations and your participation today. I hope you will join the coffee break, and I hope the participants will also join the coffee break. It'll be a bit shorter. Instead of 20 minutes, we'll just do 15 minutes to get a bit back on track with the time. So please rejoin the Zoom meeting at 3:35. It's the same link, so you can stay in the meeting or log out and log back in, and whatever works for you. Great, so thank you all, and we'll see you back here in about 15 minutes.
Thank you.
Thank you. So the first presentation will actually be done through a recorded video. That's going to be, or who you will hear talking is Sumit Sood. Sumit Sood is a third-year doctoral student at the University of Lille. He specializes in dynamic modeling of multiphysics systems and development of control and diagnosis algorithms for such systems. So I am going to share the video.
Green hydrogen is the term used to describe the hydrogen produced by using electricity from the renewable sources. Hydrogen can be stored and used for various purposes such as for producing electricity, running fuel cell-powered cars, for industrial applications, and also for producing dimethyl ether using power-to-X technologies that are being developed under the banner of European E2C project. Producing hydrogen using intermittent sources have its own challenges. The power is not available all the time, and the intermittent nature of the sources may lead to lower efficiencies and accelerated degradation of the components. The whole system is highly complex due to the presence of multiphysics phenomena. Also, due to the involvement of hydrogen gas, the safety of the system as well as the operator is of prime importance. There is a requirement of the solution to make these kind of system more efficient and safer to use. Mathematical modeling could be the answer to these challenges. Mathematical model is a set of differential equations that allows us to see the evolution of outputs based on the inputs and process parameters. Mathematical model of such complex system can be used for studying the real behavior of components, subsystems, and overall system behavior under dynamic intermittent operations in various operating conditions. A good model can not only be used for process simulations but also helps to develop control and diagnosis algorithms to run the system smoothly, safely and efficiently. The model can also be used for systems health management. Here at University of Lille, a generic dynamical multiphysics model of PEM electrolyzer running on intermittent sources has been developed using bond graph approach. The developed model has various key features. The developed model consists of submodels, known as capsules, that can be easily modified to fit any configuration of PEM electrolyzer. Because of the generic nature, it can be easily sized and scaled as per the requirement. The model incorporates the calculation of efficiency at subcomponents level to estimate the performance of the electrolyzer. Also, the system dynamics and the different thermal losses can be predicted, which cannot be done in the real process. The model can also be used for the development of control algorithms and diagnosis algorithms for online implementation. For online fault detection, the estimated outputs of the model are compared with the actual values from the real process measured using sensors. The difference between the two is known as residual and its value is 0 in the absence of the uncertainties. The non-zero value of the residual indicates the occurrence of fault in the system. However, in actual practice, the value of residual is usually non-zero due to the presence of uncertainties such as parameter uncertainties and measurement uncertainties. Therefore, in order to avoid false detection, upper and lower bounds for the residuals are used known as thresholds. In normal operating conditions, the residual do not cross the thresholds. When a fault occurs in the system, the respective residual value crosses the threshold limit and the alarm is generated. Not all residuals are sensitive to the fault occurred. Therefore, by knowing which residuals have crossed the thresholds, the fault can be isolated. Various subsystem level efficiency can be calculated in real time using developed model. As the model is based on the power exchange between different elements, one only needs to know the input power. The power at the input and output of every subsystem is known. The efficiency is calculated as the ratio of the output power to the input power, where output power is the difference between input power and the estimated power loss. With the help of real-time efficiency calculation, the system inputs and parameters can be adjusted in order to improve the performance of the system. The hybrid multi-source hydrogen generation platform, available at Polytech Lille, has been used to demonstrate the effectiveness of the developed model in online efficiency calculation and diagnosis for fault detection and isolation. The platform consists of photovoltaic panels, wind turbine, and batteries interconnected to the common DC bus presented by the electrical cabinet. This electrical cabinet contains the power converters which are used to control the power flow, and the controller used for supervision. The electrolyzer uses the power produced by photovoltaic panel and wind turbine to produce hydrogen gas, which is stored in the metal hydride canisters. The produced hydrogen can be used for several applications, such as for producing DME using the said MES process or supplying the fuel cell to generate electricity. For the implementation of the developed algorithms, data acquisition is required, which is performed using a controller and a Windows-based computer system. There is local communication between the two, which is realized to get the data of the sensor measurements and generate the control signals to act on the actuator to control the power flow between the HMS components. A GUI has been developed using MATLAB Simulink in order to exploit the developed model for real-time efficiency calculation and for supervision of the platform by generating the fault indicators for fault detection and isolation. This is the graphical user interface developed in MATLAB Simulink. This GUI incorporates all HMS components model used for online diagnosis. These blocks represent the efficiency calculation deduced from the developed models of each component. Here is the GUI in operation in real time for platform supervision. Using this GUI, one can monitor the measurements of different sensors. One can also monitor the fault indicators in order to detect the occurrence of fault and monitor the efficiency of different components in real time. The effect of the intermittency of sources on the efficiency of the electrolyzer can be seen. The intermittency of the sources does not allow a constant production of hydrogen. For the validation of the effectiveness of the diagnosis algorithms, the faults are injected into the platform and the evolution of the fault indicators with their adaptive thresholds are verified. 3 faults have been considered for the demonstration. 2 component faults are introduced by affecting the internal resistances of the battery and the photovoltaic panel. Valve blockage fault is introduced by shutting off the hydrogen flow valve at the output of the electrolyzer. This demonstration corresponds to component fault in the photovoltaic panel. To introduce this fault, we have to vary the resistance to push the internal resistance above the acceptable limits. On the right side we can see before the injection of the fault, the residuals are within thresholds. When the fault is injected, the residuals 1 and 2 goes out of the thresholds. This shows only these residuals are sensitive to this fault. The fault is injected in the battery in the similar way as it is done for the photovoltaic panel. On the right side, we notice that only the residuals 2 and 3 are sensitive to this fault as they went out of the thresholds when the fault has occurred. The blockage fault is injected in the electrolyzer by closing the valve of the cylinder during the operation of the platform. In this case only the indicators 2 and 4 are sensitive to this fault as they went outside the thresholds when the fault has occurred. According to these demonstrations it can be seen that each residual is not sensitive to all the faults. For example, the fault on the panel influence only residual 1 and 2. The fault on the battery influence only residual 2 and 3. The blockage fault in the valve influence residual 2 and 4. According to this analysis of the fault signature matrix, we can conclude that the faults can be isolated when they occur. From these demonstrations, we can conclude that the modeling is very important for engineering tasks. The developed model can be effectively utilized for fault detection and isolation. This allows us to select cost-effective maintenance strategy and we can reconfigure the system easily in order to implement robust control. Also, the model is effective in carrying out online calculation of efficiency, which allows us to estimate the dissipated power and take appropriate decision for maximizing the performance of the system. These strategies will ensure the availability of the energy. What we can offer. We can provide the dynamic model for the development of optimal operation mode management algorithms, and to carry out the study to check systems reliability. We can help for the implementation of online diagnosis and health management algorithms, to ensure the safe and efficient operation of the hybrid multi-source platform for green hydrogen production. We can help reducing the maintenance cost by selecting the best possible maintenance strategy for multi-source platform equipment, such as wind turbines, solar panels, electrolyzer and fuel cells. We can offer feasibility testing and technical and economic calculation before the installation of green electricity production and storage facilities. With our expertise and set of skills, we can help in decreasing the production costs of decarbonated electricity. We can help in realizing the online monitoring of energy efficiency. Thank you for your attention.
Great. So thank you to Sumit for making the video. If you want to have more questions or discuss the activities of the University of Lille, we'll be having breakout sessions after the project presentations. So you can join the breakout session, Multiphysics Dynamic Modeling. Sumit will be joined there by Professor Belkacem Ould Bouamama, who is also a full professor at the University of Lille and head of the Crystal Laboratory. So I will now give the floor over to Rob Stickelman. Rob Stickelman is a chemical technologist by training and is now an associate professor in the Energy and Industry section of the Faculty of Engineering, Policy and Management at the Delft University of Technology. Rob, go ahead.
Thank you, Erin. Welcome all. I have also a modeling approach. I'm interested in modeling clusters. I will explain later what a cluster is. When I go to the project we're doing, basically the project is about technology development. We're trying to develop new technology. We did some exploring research and so on. We make all the steps for technology development. And yeah, we get more information, we become more intelligent, and at the very end, we have a lot of models, MATLAB models, Aspen models, and so on. And we are quite well able to describe the technology. And of course, we hope that the TRL level is going up. This is from the viewpoint of technology. When I take the viewpoint from clustering, and I am looking at an industrial cluster, I first have to define what a cluster is. I have here an old definition by Michael Porter. It's a geographical proximate group of interconnected companies and associated institutions in a particular field linked by commonalities and externalities. So it's a lot, basically it means people are really working together. So when you look at, for instance, the ZMS or the production of DME as a technology, if you want to implement it in an industrial cluster, yes, yeah, that may be a good environment. Clusters may offer a lot of positive effects. I show you here some drivers for having distribution infrastructure, availability of various utilities and feedstock, accessibility. There's already a lot of expertise around, so it's a very positive sign. On the other hand, there are also barriers. Probably you are not the only one producing DME in the cluster because there's a lot of competition. Basically, the hardware in the system is quite old and still there. You have the old boys network, and this is not in a positive sense. It's things are already arranged, so you have to fight in your own position. Yeah. And there are some other barriers. So I'm interested. How can I couple include a power to X option in such a cluster? Then I look at, of course, it should be a good enough TRL level, and I see a business case analysis, and the business case analysis of a new technology is often about the CAPEX and OPEX and world market prices, and often that's necessary to do, but I think it's not enough, because we should also try to include all the effects of putting a new technology into a cluster. The best summary I could give was this one. I see an existing industrial cluster, everything is running and doing quite well. And I have a very, very innovative new PTX option, but yeah, I really don't know what the effect will be when I have to include that one in the system. But this is my problem. Thinking about that, then I make some discoveries. I have quite some experience in conceptual process design, making Aspen models, making very difficult models with MATLAB or all kinds of other programs. And basically my conclusion is it's all too complex to do it that way. If you build an Aspen model for a new process, it's okay. If you want to do it for a cluster, you will fail, and just because of time. The problem is that complex, so you are not able to do it in time. So what were our choices? We will model the cluster firstly as a network, so not as a A2B process, but as a network. So there are recycle flows and so on. And we use processes and products. That is our distinction. We have processes and products. And we will simplify. We will just simplify everything. Even sometimes maybe you will think it's too simple, but we want to have linear relations. If you are designing a process, yes, Aspen is very useful because you can just find the best way to the best process. At the very moment the process is running, it's basically doing the same for a long time. So then you can choose for linear relations. So this is our approach, and Yeah, we still include time series, so it's somehow dynamic. It's dynamic in one direction, as I call it. And we also include owners of processes. And now, the final trick we do, and this is basically, I think, the strong part of our approach, we use a program called Linear, which is a graphical user interface that makes it very, very easy to build mixed interlinear models. And it's a graphical interface. You just place processes and products on a sheet, and the model is there. So you don't have to really bother about the model. Now, this is an example of a model structure. So this is not a model itself, but a model structure. Now, what you see over here, that I have some, on the left side, some inputs, on the right, some outputs, and all the rectangles are processes, and the ovals are products. And now, what this is somehow a picture of what we are doing in the project. We have several markets for electricity, CO2. We have several products, formic acid, DME, even hydrogen. We have some what we call technology configuration. That is the ZMES process. It's two other processes that are studied in the electrolyzer. And finally, and that's relevant for this scheme, we have cluster options. And the very products I just pinpoint by these symbols, yeah, these are typical what I call cluster connections. For instance, CO2, if you use, what will give you the CO2? If you use hydrogen, who will produce the hydrogen? For my opinion, hydrogen is hydrogen if it's produced in a green way, or even if it's imported from Oman with a tanker. I don't mind. Hydrogen is hydrogen, and the hydrogen is available in the cluster. So, with this, in this manner, I am able to connect the new ideas to the cluster. And behind this are all submodels, and I will show you more in the breakout session. This is a little bit how we create a what I call a mixed interlinear programming model, only with linear relations. Yeah. What did we do up so far? We choose the clusters of Rotterdam and Antwerp as our cases, and we already partly modeled part of those clusters. We have a baseline for markets, and we have, of course, models for the PTX options from the project. And now I'm busy implementing the portals and the high transport projects in the system. And now I show a lot of model deliverables. I will not name them all, but basically we are able to show all kinds of products and financial flows in the model. This is a little bit what I have to tell in this story. If you want to hear more, then you are welcome in the breakout session.
Great, thank you very much, Rob. So Rob will be running the breakout session assessment of DME Power to X options. So please be sure to join that session if you'd like to hear more and discuss more with Rob. So we will move on to the next presentation. This will be from Peter Sanderson. Peter Sanderson is a postdoctoral research associate in the steering group at the University of Sheffield. He's been working on policy-related issues for multiple Power to X and CO2 utilization projects. Peter, are you there to go ahead and share your screen? We do not see you or hear you, Peter.
There, how about that?
Yes, perfect, thank you. Go ahead.
Right, I'll just make it on the slideshow and then I'll be with you. Sorry.
No worries.
I think it's sharing, but it doesn't seem to be going to the slideshow. Oh, there we go.
Yeah.
Right, I'm going to give an introduction to what we're doing to carbon footprint the Power to X DME process. So as part of the E2C project, there wasn't actually a deliverable designed to do a full LCA. So we realized that that was missing in the project. So what we've done is got a master's engineering student to do his research project, working out the carbon footprint of the DME process and the formic acid process. So just as a reminder to anyone who's not an LCA expert, LCA is a way of finding out the environmental impacts of a process. And basically what you need to do is identify all the material and energy inputs into that process. So for these processes we're looking at, it's basically looking at the chemicals, the catalysts, electricity, heat, and water. Also, you need to take account of the infrastructure, such as the equipment used. Once you start doing that, you realize that you need to look at the energy used to create that infrastructure and transport it to site. And that might mean looking at the steelworks. It can be quarrying the iron ore, or even going as far as looking at the power station to generate the electricity which was used in the steelworks or in the quarry. So before long, an LCA can really get out of hand. You need boundaries. Thankfully, at the moment, there are inventories out there which have got pre-calculated data, and that limits the amount of work that's involved. So thankfully, we're not doing this for the first time. We're standing on the shoulders of giants, if you like. So these inventories allow us to deduce that things like processing 1 ton of steel or producing 1 ton of steel requires inputs of, and all the different inputs will be listed. That is what an inventory is. Then that inventory is used within LCA software to identify the environmental impacts, so that producing that 1 ton of steel has a global warming potential of X kilograms of carbon dioxide, for instance. If you're doing a full LCA, you need to take account of all the other environmental impacts, such as acidification, ecotoxicity, human toxicity, ozone depletion. There are a wide range of different environmental impacts involving water, land, air. We decided just to focus on the carbon footprint, because that is the driver for most Power-to-X technologies. That is the reason for doing them. So we've used an EcoInvent database with this SimmerPro LCA software. In order that the student that we got to do this work, so that he wasn't spending so much time modeling the capture of the CO2 for use in the system, because the E2C research, the pilot development program, they're not actually focusing on the carbon capture process. They're on converting the carbon dioxide into useful products. So we decided to use literature sources for the source of the carbon dioxide. And so, as Arne mentioned in his talk, we've used the same literature article that he was talking about from the Arkham research group, and they identify carbon dioxide captured from the bioethanol plant, which is the most highly concentrated source of CO2 widely available. Then you've got the most dilute source of CO2 is from direct air capture, and that obviously takes a lot more energy to capture that. For the PEM electrolysis step, we've used EcoInvent data, which has been scaled to the electricity use and made more applicable to the type of PEM electrolysis we're doing. So we've done a little bit of modeling, but we're using black box systems basically from the EcoInvent database. However, for the sediment and purification processes, or the downstream processing, we've actually used the modeling which the TNO team did for the business case analysis. They've written business case analysis for DME and for formic acid already. So we've used their modeling, and the benefit of that is that the carbon footprinting will actually fit quite nicely with the business case analysis, because it's using the same assumptions. The final assumption is that we're using DME as a transport fuel to replace fossil-based diesel, for instance. Now, as soon as you start doing an LCA or a carbon footprinting process, you start realizing that there's so many assumptions that have to be made. So for instance, we're assuming that the CO2 captured from a bioethanol plant is this minus 0.94 kilograms. So the footprint of the carbon dioxide is almost -1. And Arne very kindly mentioned in his talk that in an ideal world, if you're capturing 1 kilogram of carbon dioxide, its footprint would be -1 because you're removing it. Obviously, the footprint never is -1. From a bioethanol plant, the concentration of the CO2 is something like 97% pure. So there's very little extra processing you need to do. Therefore, the footprint when you're capturing it from such a place is very low. However, using direct air capture, the footprint is significantly larger. Both of those footprints, of course, depend on the carbon intensity of the electricity you use to capture it. So that adds an extra complication, but I'll explain later on how we can get around that. We don't worry too much about that. We've looked at the electricity from 6 different sources. We looked at the electricity sourced from the 4 E2C nations. So that's the UK, the Netherlands, France, and Belgium. And also electricity sourced from offshore wind and solar PV. And another assumption which is worth mentioning is that because in reality, the process isn't 100% efficient. So some CO2 and some hydrogen is actually left over in the reaction vessel. So we're assuming that is recycled back into the reaction vessel, as well as the carbon monoxide, which is formed, that's recycled back. However, when you're doing an LCA, you have to decide what you do with all these other residual compounds. And there is a small proportion of methanol which is produced. We've decided it would be sold. Now that when you sell that methanol, it actually avoids the production of fossil-derived methanol. So it actually gives you a slightly negative carbon footprint. Usually I don't like doing this sort of thing because I don't want the LCA to have lots of unobtainable and unlikely circumstances. I've read too many LCAs like that. However, in this circumstance, it's only a couple of % difference. It doesn't make a massive difference. So we've gone with it and we've just said, right, we'll extract this methanol and sell it as a product. But as I said, it doesn't make a great big deal of difference. So when it comes to analysing the results, what we're doing is analysing it in terms of whether we would gain support through the Renewable Energy Directive. Because in Article 25 of that directive, it says that you've got to achieve greenhouse gas emission savings for these so-called renewable liquid and gaseous transport fuels of non-biological origin. You've got to achieve a 70% reduction in emissions from 1st of January this year. So the emissions goals have been changing, but at the moment it's 70% you've got to achieve to be able to get some sort of subsidy support through the Renewable Energy Directive. Now, Annex 5 of the directive tells you how to calculate your greenhouse gas impacts for biofuels and bioliquids. However, there's nothing published yet for these renewable fuels of non-biological origin, or let's call them e-fuels because it's a bit shorter to say. There is a delegated act due by the end of this year, but I believe in July of this year, we're going to get a new version of RED published. There have been a few leaks about it already. So whether the version in July actually talks about these greenhouse gas impacts, I don't know. But for biofuels, when you're comparing against your fossil fuel comparator, they advise you to use a comparator of 94 grams CO2 equivalent megajoule. So I think we've got to assume that the e-fuels, you'll be using the same comparator. So when you compare against that, it does appear that the SEDMAS process developed by E2C, it will achieve this 70% reduction, but only if you're using low carbon electricity. As with many other Power-to-X processes, if you try and use grid electricity, you won't achieve the reduction required. Also, you need to use carbon dioxide obtained from a concentrated industrial source because that has the lowest carbon footprint. It would be possible to use direct air capture, but that would have to be used in conjunction with renewable energy itself. So if you're using a direct air capture produced commercially and you're just purchasing carbon dioxide, as there have been some models for that, then that wouldn't work if they are using grid electricity. That would have to be from renewable electricity. So the way this is the last slide now. So the way we're analysing these results is to analyse it in terms of getting support through RED 2, as I mentioned. We're going to look at it in terms of what does the carbon intensity of the electricity need to be? Because we've looked at the six different sources of electricity, 4 different countries plus solar and offshore wind. So that you can actually plot a straight line between the carbon footprint of the DME and the carbon intensity of electricity because the two are directly proportional to each other. We can also do a similar thing when we're looking at the carbon footprint of the carbon capture process. So as I said previously, I don't get too worried about people saying, well, what actually have you modeled for your direct air capture? What is a capture footprint? Because every 6 months or so, every year, there seems to be a slightly different variation of direct air capture or other carbon capture methods, whether it's for liquid solvents or solid state capture systems. So I would prefer to present the results in terms of what does the footprint of the capture need to be in those sort of terms, rather than just making assumptions. So it'd be interesting to look at whether this informs our choice of different potential locations, because there's no doubt that the Port of Rotterdam must be a top spot for any Power-to-X process, because the Port Authority is itself acting effectively as a project manager. They're organising blue and green hydrogen production projects, so it's likely in the future that they may well have a hydrogen pipeline network, and they're organising carbon capture and storage projects at the port. So it's also possible there's going to be a carbon dioxide pipeline network in that location. So you can't deny that's got really favourable infrastructure. However, the local carbon intensity of the electricity grid is the highest of all those 4 2Cs nations. So you could say, well, why don't we just build this plant in France, because they've got the lowest. They've got a carbon intensity of something like 50 grams per kilowatt hour, as opposed to over 200 grams for the Netherlands. However, that doesn't really matter, because in RED 2, they talk about additionality, in that new renewable electricity is required. The European Commission are adamant that they don't want to effectively subsidise the transport fuel sector reducing their carbon footprint at the expense of other industrial sectors, because that's what would happen if transport fuel was all made by Power-to-X processes, and all those processes took all the existing renewable electricity, then all the other industry would have to use fossil-derived electricity, because at the moment we're not 100% renewable. So yeah, at the moment, RED 2 is saying you need to produce additional renewable energy. So that is another hiccup to be got over. Finally, we're going to use the results of the LCA to try and suggest when future research should focus on. So obviously, electricity prices is kind of out of scope for the E2C project, but it would be good to know which process steps within the DME production and the formic acid production, which contribute most to the carbon footprint. So that's the way we're going to be analysing it. Hopefully in the next few months, we'll have the full results. The LCA, or carbon footprinting project, has just finished today. The student has literally just submitted his research project today. So these results are sort of hot off the press. We will be producing specific reports for the E2C project, and hopefully we'll be sending those out to interested parties in the future. But at the moment, we still need to decide whether we're going to try and publish this separately through research journals. So that's why at the moment I don't want to give the precise results, as it were. But okay, I think that's all I was wanting to say there. So thank you very much. I will stop sharing my screen.
Great, thank you, Peter.
Thank you.
And I put it in the chat, but Peter will be in the breakout session, Carbon Accounting and Scenarios. So please join him there if you'd like to discuss further. So we have one more presentation from the E2C project. That'll be given by Carlos Sanchez Martinez. Carlos completed the PD engineering program in process and product design at TU Eindhoven, and then joined TNO Energy Transition in 2018, where he started working in the Sustainable Process and Energy Systems Department. Carlos, go ahead.
All right, thank you very much. Can you hear me?
We hear you, yes.
All right, so let me start sharing my screen. And you can now see it? All right,
yes,
so perfect. Good afternoon, everyone. As Erin said, my name is Carlos Sanchez Martinez. I come from the Delft branch of TNO in the Netherlands. And today in this plenary session, we're going to discuss the techno-economics of Power-to-X implementation. So let me start putting the laser pointer. All right. So just a brief recap of the E2C project. Well, as you all know, the E2C project is focused on the development of Power-to-X or PTX technologies that are capable of utilizing both renewable energy and waste carbon dioxide streams from neighboring industrial clusters in the 2Cs region. So basically, the Power-to-X technologies developed in this project will be able to convert CO2 into valuable fuels and chemicals and reducing greenhouse gas emissions at the same time. So said Power-to-X technologies are the so-called direct route for the formic acid production and indirect route for the dimethyl ether or DME production. So the question that we want to answer in this plenary session would be, what is the point of performing a techno-economic analysis at such low technology development levels? Well, there are various relevant outputs coming from a techno-economics analysis, and it would be, first of all, to identify the major cost drivers and critical process parameters at an early stage to steer R&D efforts. As well, we can evaluate whether the process can potentially be economically attractive. And as well, we can pinpoint the most crucial variables when moving up in the scale. So for instance, just as an example, what would be the impact of CO2 availability at high production capacities in a hypothetical PTX plant? And as well, we can use the techno-economics for comparison with traditional fossil-based processes to identify potential gaps in the performance of these PTX technologies. So we can now move to the direct route for the formic acid production from CO2. So this direct route will be relying on this direct electrochemical reaction of carbon dioxide with water, along with electricity as the main input, to produce formic acid and oxygen. So oxygen is a byproduct from water oxidation happening at the anode of the electrolyzer. So as you can see in this diagram for the direct route, you see that we have two distinct lines depending on the type of electrolysis we choose. So on one hand, we have what we call the 3-compartment electrolyzer that is being currently developed at TNO Delft. On the other hand, we have the 2-compartment electrolyzer that is being developed by Vito, that is our Belgian partner. So the main difference between these two approaches in the electrolysis is that on the 3-compartment electrolyzer, we will produce formic acid in its direct form. And in the 2-compartment case, we will produce formate, which is the deprotonated anionic species of formic acid. So because of this, in the 2-compartment electrolysis case, we will need to add a protonation step to produce the formic acid out of formate and then go to the separation, to the purification section to produce the concentrated formic acid solution. So indeed, this will have an impact on the final process economics and the total production costs of formic acid in the 2-compartment system. As you can imagine as well, that the electrolysis process in the direct route is the most important process, cost and technology-wise. And therefore, the determination of the optimal conditions or process conditions is then critical for the economics. So how to find said optimum performance? So in this graph that you see here plotted, we have the total production cost, that is the black line, along with the OPEX line, so the operating costs line for the electrolysis process, and the CAPEX line, so the capital investment per unit of product line, versus the applied current density. So the applied current density is a really important parameter in an electrolysis process. And as you can see, the dependency with the operating costs is linear with the current density. This is dependent on the cell voltage that is applied. And also, as you can see, the CAPEX is reduced with the current density because the CAPEX is related to the electrode area, and it benefits from a higher current density due to a higher productivity per unit area. So this means that for the same area, we have a higher production rate when we increase the current density. And the total production cost, it would be the combination of both. So you do see that we can find a minimum in the total production costs for formic acid at a certain range of current density. So that means that with this analysis, we can identify a range of optimal process conditions that can be applicable for the electrolysis process of the direct route for a higher scale electrolysis process. And this is the optimal conditions we will choose for the later economic analysis. So once we have chosen these optimal parameters, we can then run sensitivity analysis on both the process parameters and the economic indicators. So in the process parameters, we see that the Faraday efficiency, which tells us how many electrons end up in our desired product from the total electron input, and the yield of the electrolyzer, which tells us the product loss during electrolysis, are the dominant cost factors. So these results can already tell us and can already flag the R&D researchers and departments to pay special attention to catalyst and electrode development to enhance the efficiencies. and as well for the reactor and process development to try to minimize as much the formic acid losses in the electrolyzer and to increase its yields as much as possible. On the economic indicator side, we see that the annual production scale and the electricity price are the main cost factors. So if you look at the annual production scale, we must understand that for bigger plants and for bigger processes, we can benefit from an economy of scale effects and reduce capex per unit of product. On the electricity price, it is a straightforward relationship with the cost, given that the electricity is one of the main inputs for the electrolysis process in the direct route. So the main message here from the sensitivity analysis would be that we must look at low electricity prices. So for instance, using excess renewable electricity, and also try to have high production capacities in the future Power-to-X plants. So now if we would go to analyze the main results, economic results from the direct route, we see that if we would compare first the benchmark market price fossil-based formic acid with either the 3 or 2 compartment case for the direct route PTX technology, we will see that already on the base case, the total production cost is only 5 to 10% higher than the benchmark price, which is already really good news. Secondly, we would focus just on the comparison between the 3-compartment and the 2-compartment systems. We would see that the 3-compartment case performs slightly better than the 2-compartment system. This is due mainly to the fact that the presence of this protonation step in the 2-compartment electrolysis is adding a huge cost in the final separation costs on the overall system, even though the electrolysis would perform slightly better in the 2-compartment electrolyzer. And third, if we would take the best case, most optimistic scenario parameters that we've identified in the previous sensitivity analysis, and we will apply that to both the 3-compartment and the 2-compartment systems from before, we would see, and we run another economic study, we would see that we can achieve really good economic figures, having up to 43% investors' rate of return on the direct route 3-compartment electrolyzer system. So this means that the direct route Power-to-X technology has a great economic potential. So that would be my take-home message for the direct route. If we would now go to the direct route for the dimethyl ether production from CO2, the reaction that will take place would be the combination of green hydrogen produced via electrolysis plus carbon dioxide to produce dimethyl ether and water. So this reaction, as you see, it will have a maximal theoretical efficiency for hydrogen of up to 50%, given that half of it would end up in the form of water. So this reaction will take place in the so-called ZMES process, that is a proprietary technology being developed by TNO in our patent branch. And then the DME solution that we will produce will directly go to the separation process to produce the field grade purity required for selling DME. So ZMES stands for Sorption Enhanced DME Synthesis. So in the traditional process, DME is produced through the 2-step methanol production and dehydration route. So the particularity of ZMES is that we can remove in situ the water that is produced using adsorbent materials, and thus we can shift the reaction towards DME production. If you remember from the previous reaction, it was an equilibrium reaction in which we need to shift the equilibrium towards DME. And so the ZMES process works in a stepwise fashion using a column arrangement as you see here. And the operation can be optimized with a cycle design, balancing carbon selectivity, yield per pass, productivity per column, etc. So analogously, with the direct route, the found optimal parameters for ZMES are used to run the economic assessment. So if you want more information, by the way, on ZMES technology, you can check these 2 papers that are explicited here. So if we now go to the economic analysis and the main results for the indirect route, we would see that on the left-hand side, the breakdown for levelized DME costs display a huge gap in between the benchmark field-based DME cost with respect to the indirect route total costs. So as you can see, only the electricity price is already greater than the market price. So both this one and the capex related to the hydrogen electrolyzer demonstrate the extent by which hydrogen production determines the feasibility of the indirect route for dimethyl ether synthesis. If we remember from the previous slides, at least 6 moles of hydrogen are necessary per mole of DME. So the optimized sadness process, we must say, that uses hydrogen very efficiently and can actually maximize the hydrogen yield towards DME to minimize electricity and the capex of the electrolysis costs. So we can say that the sedments is already performing much better than other technologies that uses hydrogen for DME production. As well, you can see that the capex for for the DSP and the separation cost and the sadness columns are quite limited. So this process, we can then say that is really limited by the hydrogen production capacity and the hydrogen production costs. On the right-hand side, we can see the influence of various parameters, and we do see the electricity price that is mainly influencing the hydrogen production, and efficiency of the hydrogen electrolysis is already determining greatly the economics and the feasibility of the direct route. As well, we see that the CO2 price is also quite important, given that we need at least 3 moles of CO2 per mole of DME. So the main take-home message here from the direct route is that we need to cut down costs from this process. So how can we do that? So we have several options. That would be, first, to revalorize the oxygen stream that is coming from the hydrogen electrolysis process by selling the oxygen produced, increasing the hydrogen electrolysis efficiency and lowering down the capex by using more affordable catalyst materials, subsidizing the CO2 utilization by having zero costs for the CO2 or even negative costs for CO2, or also lower energy prices by, for instance, using excess renewable electricity that will come even on cost for free. So that will be the end of my presentation. Thank you very much.
Okay, thank you, Carlos. Good. So now the next point on the agenda is these parallel or interactive parallel sessions. This will be run through breakout rooms through Zoom. Let me just share my screen so everybody knows what those are. Good. So there's now, the breakout rooms are now open. I invite everybody to go ahead and choose. You can decide which one you would like to join. And we'll go ahead and do half an hour discussions. We're running a little bit over time, but we can do discussions of half an hour, and then we can rejoin the meeting at 4:55. I will send a announcement, I guess you could say, 5 minutes before the discussions will wrap up, and then you'll have a minute to rejoin the meeting. Then the rooms will be closed automatically. Great. So please go ahead and join, and put a comment in the chat if you have any problems.
The E2C project of this year, where we tried to show you the developments of the project and also to connect with stakeholders from this field, and to get a broader understanding of the challenges that lie in the development of these technologies. Of course, the communication activities in the project are not going to stop with these events. You can join us for to get newsletters from the project, but also what we would like to understand from you is how you have enjoyed the events that we have organized. So please use the poll before you go. After this closure, there will be also the possibility of further networking and discussion. So you can use this this platform as well. If you have feedback for us, we will be happy to receive that, and we will react to it. So I'm curious to see the comments that you will leave in the survey of the event.
This is just to show everyone how you get to the polls. Sorry to interrupt you, Annika.
Yes.
If you go through the Hoover app, then you will see, yeah, under resources, then you will see polls. So we have a few polls going just so you can leave your feedback there. So.
Thank you very much. So as I said, we are going to communicate still the results of our projects via newsletters. You can also follow us on Twitter and on our LinkedIn page. You can also get involved. So in case you are not one of our observer partners, you can contact us and become an observer partner of the project. In this case, you will get invitations to extra events which are dedicated to our observer partners. A special event is going to be organized by the project, especially targeting students and postdocs, and that will be the winter school, which will be held on the 7th and until the 11th of February of next year. We want to have this as a face-to-face event, but we'll have to see towards that time how if we are able to meet fully face-to-face, or if we'll have also partly online. And this being said, I wish you a nice discussion in the next coffee room, and hope to see you also at our next events. Thank you very much. This is for me.
Yes, great. Also from my side, thank you everyone for joining. Thank you again to all the speakers. I hope everybody enjoyed the event and the discussions, learned something as well. And as Anka said, we hope to see you at a future event. Yeah, be sure to sign up for the newsletter or follow us on Twitter or LinkedIn so that you are kept up to date with all the project events and other news, of course. Great. Have a great day, everyone.
Thank you.
Bye. Thank you.
Thank you. Bye-bye.